Почему мы решили сделать на английском? Потому что докладчик может сказать больше. Потом это будет запись, вы можете перевести его сами впоследствии. Значит, я хочу представить вам президента Международной ассоциации компьютерных наук в спорте, доктора, профессора Мюнхенского технического университета Мартина Леймса. Давай.
Так что я переводить должен, на русский или нет?
Представляй, профессор.
So Martin, it is your turn. It is your turn to announce your presentation for us. So you just may go. Сейчас чуть-чуть надо проверить Мартину, может он не ту презентацию выбрал. Поэтому чуть-чуть подождем пару минут.
Коллеги, все здесь в основном математики, вы понимаете.
Ну, мы типа, Егор Анатольевич договорился, что не будем на русский переводить, наверное.
Да. Представь, докладчик Мартин Леймс, профессор, доктор Мюнхенского.
So Martin Leyms is a professor in Munich Institute of Technologies. He is also a chairman of International Association of Computer Sciences and Sports. You know, our foreign guests, of course, might know him. So, Martin, it is your turn. Yes, start.
Yeah, thank you very much for the invitation to speak here, and also for the promising contacts to our association, the International Association for Computer Science and Sports. We had some very nice days here at Moscow already. We enjoyed a tour to the Kremlin and to the city, but now it's the time of working, and I will give you a presentation of performance analysis in football. I was asked to speak about this, although this is not directly a sport here at the center. Okay, let's start. This is a picture I brought with you because there's of course a big event in 2018, the World FIFA Championships at Russia, and this is a picture of it's from 1966. It was the biggest success of Russia in a FIFA World Championship. Since then, it was a half final, and this is Lev Yashin, this is the goalkeeper, and also Uwe Seeler, a famous German player, and they were competing 96 in the half final. And I would find it a great thing if this would happen 2018 again, that Germany and Russia meet at the half final, like they did in '66. But experts told me that's only possible to meet in the final between Germany and Russia. So let's make it to the final. Okay, good. This is my program for today. I want to give a short introduction. I want to present a study, introduce myself, and I want to present a study on that we conducted in technology in football. Then I want to go into two areas I'm doing research in: practical performance analysis, that means performance analysis with athletes, and theoretical performance analysis, that means thinking about the structure of sports, modeling sports, and so on, and finally some conclusions. Okay, first introduction. Myself, my research areas are training science with special emphasis on game sports research, and today I will have a focus on football. And of course, sport informatics is a research area of mine. And there is, the position is already mentioned. Right now I'm the elected president of IAX, the International Association for Computer Science and Sports. And this is a recent picture drawn at Zurich. And in Switzerland they founded the National Swiss Association for Computer Science and Sports. And so as a president, I'm very happy that there's so much interest in joining IAX. Then I'm speaker of the German Association for Computer Science and Sports, and maybe of interest for some of you, I'm also thinking about the future of giving scientific support to German top-level sport, and this is also one of my duties in Germany. Practice collaborations, we are doing game analysis, we are supporting national teams in game analysis, for example, beach volleyball, goalball, which is a Paralympic sport, and table tennis. We developed match analysis software for those teams. Maybe you remember that Germany was successful in that Rio, where our female team won the gold medal, and in London our male team won the gold medal in beach volleyball, and both were working in the background with the software we developed. And in handball we are doing video tactics training with a female team. Then in football we used to have collaboration with Bayern Munich, the best German club, with position detection, when there was a coach that was very much interested in that. And currently we worked with the first league team in a doctoral dissertation on match analysis, and today we are working with the first league team also in diagnostics. Good. So my first chapter will be on technology in football, and I will show you a study we conducted. And first let's talk about technological progress. Yeah? And these are the official balls with where the FIFA championships were played with from 1930 to 2014. And you see at one glance that there is technological progress in football. What are new developments we are dealing with? New developments we have in football, especially, or in sport in general, we have new developments in position detection. Yeah? Since 1 decade or more, a little bit more, we are able to track the players on the field, either by video, by GPS or radar, and this gives us new options for performance diagnostics. We can study the load of the players during match, as well as the formation of the players during match, and this has given rise to much research in this area, and I will report on these activities also in my presentation. Another development that is important for my work especially is that performance analysis is used more and more for media enhancement. Yeah? The broadcasting company enrich their reports on matches using statistics or special graphs, yeah, that are produced by performance analysis. And this is a tradition in the United States, and it will become more and more important in Europe, and also in sports that were not affected by this so much before. This is a very interesting trend. And of course, we have innovations in sensors. Yeah, we see, for example, we see the 9 degree of freedom inertial measurement units with 3 degree of freedom accelerometer, gyroscope, magnetic field sensors each. That gives us new options for analyzing the performance, because those sensors are very small ones, and we can use them during match to analyze performance in match. And also a new generation of sensors is ready to be introduced in game analysis, to be worn during the games. These are biosensors, where we get not only heart rate variability, breath rate, and many other biological values from those sensors, and this will be very interesting for the future of performance analysis. But we still have problems in this area, and this is these are our duties where we can work at. One problem. Oops. One problem is the pointer. Yeah. We have more and more commercial providers of sensors and diagnostical tools, and collaboration. These are not scientific institutions, and collaboration of them has some special conditions, and one must be aware of that. Then it's a difference. We have different purposes of data acquisition, and it's a difference whether you perform data analysis for the media or really to give support in practice, because these are simply other questions, and for the media, in my experience, things have primarily to look very nice, and whether it's very accurate, very valid is only in the second row of importance, and which is not the case when we want to support real athletes. So, and the question is still open, whether the data are precise enough, the reliability question. And now, when we want to give real support to practice, we have to analyze the potential of this new technology. Yeah? Does it provide really information that create new insights that help us to train better and to perform better? Or are these just things that look very nice and do not help us, something of decoration? And this is a question that has to be addressed by sports science. And when there's a positive answer of this question, we have to come to the next question and ask ourselves, is practice capable to work with those new instruments? Yeah? And this is also not always the case. So there's many things to think about, and this is of course also an issue for computer science and sport informatics. Yeah, there are many relationships to these questions in our discipline. Okay. Now let's come to a study we conducted in this vein to test the reliability of diagnostical instruments. There is the FIFA quality program for what they call EPTS. These are electronic performance and tracking systems. The technical commission approved the use of wearable technology in principle in 2015, before it was not allowed to wear sensors on the body of the football players. And IFAB has two conditions still. Data cannot be used in real time within the technical area. This condition shall drop, hopefully, when everything is approved. And systems, of course, must not pose any danger to anyone in the field of play during the match. So, and this gave rise to a mandate to FIFA for launching a quality program for EPTS. And we conducted a study in this area, and I want to present you very briefly this study. We have 3 EPTS technologies at the moment. We have video-based tracking systems in football, GPS, and radar-based systems. And we have many competing providers in this market. And we conducted a study to test those different technologies for position detection. And what is rather the exception in studies until now, we wanted to test it against the gold standard, something like ground truth. And when we started to do so, we found out that it's also a demand that an EPTS testing methodology as such is developed. So then we went to look for a place where we could, for a stadium where we could test those 3 technologies, radar, GPS, and video technology. And we conducted this in the Rosenau Stadium in Augsburg. It's you have to find a place where all those 3 technologies work quite well. And for example, GPS does not work under a roof, and radar is very sensitive to high metallic tribunes. Yeah, and video needs a very steep angle. Yeah, and so as you see, it's a wide open stadium we found there, and we constructed at this place here. We constructed this scaffold, adding another 12 meters of height for the video. And you see up here the video camera is fixed. So after having a place, you have to decide which exercise you test. And we let players execute a sport-specific course. to find out very much in detail how the systems react in certain situations, acceleration, deceleration, curve runnings. We had a shuttle run and a small-sided game. Our sample were U19 football team player from German First League, Youth First League, of course. And our gold standard was the Vicon system that was used, and we extended the system to a 35 camera system, and our measurement volume was a 30 times 30 meters square on the field. Yeah, and we brought up there the 35 cameras, and some of you might know that Vicon is a device that is meant for lab settings. Yeah, so this is rather a challenge. For example, you have to do it in the night because in sunlight the infrared sensors are not working. Okay, we attached 5 markers per player, 2 on the shoulder, 2 on the pelvis, and 1 on the tailbone to have the center of mass. And the shoulder, the midpoint of the shoulders, because most of the sensors of the devices are fixed at the center of the shoulder. So, and we wanted to control them. Of course, we tested our ground truth also, yeah. And this is the result. We moved the calibration rod through this 30 times 30 meters, and calibration rod with known dimensions. And we found out that different areas of this field, we had smaller error and larger error. You see in most problems right here, at this spot in the field. But when you see at the scale, the 10 up here, this is 10 millimeters. That means our gold standard had an accuracy of sub-centimeter accuracy, which we were very happy with, because the other systems were expected to have 1 dimension higher, the errors in 1 dimension more. Some things we had to care for in the data processing in this specific study. The first thing is gate neutralization. When you measure the position of a player with a very accurate device and with a high measurement frequency, you find results that look like this. Yeah. Yeah. What do you see? Oops. Help. Oh. Okay. Short reminder. Okay. Now on, the blue line. Okay.
Как?
Okay, I try my best to entertain you. When you have a very precise device and measuring with a high frequency, the movement, the walking and running of the player, you find, maybe you saw that the curve will be, have this, will be a sine wave in a way, because at each step, yeah, you decelerate and accelerate, decelerate, accelerate. And when you have very precise gold standard, this has this deceleration, acceleration in it. And the devices that are used to detect the positions, they have a lower sampling frequency. Yeah, they cannot detect those impulses per step. So it's a little bit unfair to compare them with that. And so what we did first, we smoothed our gold standard to have a fair comparison for the other systems. And this was what we called gate neutralization. We neutralized the gold standard signal for the contribution of each step. And then it was much more appropriate. And the second thing, we had to invent in data processing was to come up for the natural body sway. Yeah? If you have a very precise gold standard for position detection, it will record a movement. Yeah? This is a movement, although the feet are staying still. Yeah? And so we do not want to have this, where the athlete is really staying still, counted as distance covered. Yeah? And so we have to come up for body sway and movement in this movements that were due to those let's say microscopic movements, because we want to have the test for the macroscopic movements with our systems. So now I want to come to the results of the study. There are impressive bar charts.
You can explain very good.
May I ask a question?
Yeah.
And what is the sense of measuring the movement using policies? What do you want to compare with GPRS results?
Yeah,
With GPRS results.
if you want to find out how precise GPS is, yeah, you need to have something like ground truth. Yeah? If you say it's an error of this size, you have to have something you can rely on. You can compare the GPS and
what is the difference?
Yeah.
Big difference between the GPRS and video movement?
Yeah, partially it was. It was up to 1 meter difference. Up to 1 meter, and the systems are quite different. And this is the result. We have different categories. For example, the precision of the XY position, yeah? Player on the field, depends very much on the technology. The largest distance we have in GPS. Yeah? The second is video-based position detection, and the most accurate one is radar-based. Yeah?
Radar-based is more than GPS,
Yeah.
yes?
Yeah. Yeah. And the second thing is the accuracy of velocity. And there the order is a little bit different, because GPS works with the Doppler effect to record the velocity, and this makes the GPS more precise what velocities are concerned. Yeah? And there the worst one with velocities is video-based position detection, and almost the same. There's almost no difference now between GPS and video. No, video is bad. GPS and radar. Yeah. And the third comparison we did is the typical performance indicators that are reported. Yeah? For example, distance covered, yeah? And also the how many meters covered in certain velocity intervals. Yeah? We compared those also for the three technologies. And there we find out that we have, especially in the measuring of high intensity movements, we have very large problems with GPS. Yeah. And also the result of the other devices say that there is still room for improvement, and they should improve very much, because the periods spent in high velocity are important for the diagnostics of the traps, yeah, because they want to really measure how often and how intense is the high load. And we found out that the systems we were testing are not very precise on that, which is a critical variable they were choosing. So. And this is also a thing. This is also a task for sport informatics. Yeah? We have devices working with computer science, with those things, and we want to check the reliability of those devices. And I'm hoping very much that will become more and more common. Yeah? That those devices are really checked for their accuracy, because you cannot, as a sports man, you cannot rely on the things the manufacturers tell you. For example, radar tells you 2 to 3 centimeters accuracy, and we found 20 to 30. Yeah, so it's a good idea for independent checking of this accuracy.
And what is the cost of each system, video, radar, and GPS, to be installed in one stadium? We own a radar system and a GPS system. The GPS is about 50,000 euros. The radar system costs about 85,000. Yeah. The video-based systems are not on the market, yeah, because the companies use them to analyze football, yeah, and so they are unique installations. They're not on the market. Yeah.
But the problem of video system is that the number of points in sensor is 120, 1,200. It's small resolution, very small resolution.
It depends on the cameras.
Yes, it depends on the cameras, and it's far from the field. It's very difficult.
Yeah.
It's necessary to have not 5, maybe 25 cameras around all the stages.
Yeah, this was very interesting for us also to see that the systems that are actually used for position detection in professional football.
Determination of each athletes when cross each other when they leave the field, that is a great problem.
This is a problem.
It is necessary to compare results from GPRS, you receive it immediately. And a lot of hours when you're spending to measuring video systems. It will take you a lot of hours and a lot of people who will analyze it, because it's necessary to divide much gain to the 15 minutes. Your first 15, your second 15.
Yeah, I know the systems that are now introduced in measuring professional football, they are live systems. You get the data live, or very fast. Yeah. But you are right. They need manual interference. Yeah. So they are half automatic. The radar and GPS are automatic.
I ask you because we also want to do it in soccer, but it's a real problem. Camera position, staff who will manually document the results.
I mean, there are companies that do it for you, and it's a good advice to check them.
Yes, let's talk about it.
But at the companies, they say we are allowed to sell the data. We make it for free to you. Okay. And the video-based position detection is only the second best choice. And as long as they might have sensors, it's the only alternative. And so this makes the second best choice, the short choice that is in place right now. Okay. Coffee break?
Dr. Lavis, I have a question to you. What do you think, how will it affect the future of football? And what will it bring to the field, and how it will be changed?
Yeah. This is a very interesting question. In Germany we have the discussion, and the buzzword is laptop coach. Yeah. And the future of coaching in football is that they all have their laptops, all information coming in, and those who are the best informatics and those who work with this information are the best coaches. Yeah. And I do not think so that it will replace.
Mostly for prognosis, for prediction, yes?
Not just for monitoring, yeah, and try to find out, of course, when there's a problem, yeah, to find a solution. What they're doing now is the same thing. They're watching, and if there's a problem, they try to take a measure. But now, in future, they will have this information where they may conduct very in-depth analysis of the problem,
and maybe better arrive at better solutions. So this is my personal memory test.
Maybe individual prediction of success, individual ability.
Yeah, there's a very interesting relationship between individual abilities and what we measure in the field. Yeah. There are some paradox results because, for example, in British Second League, they run more than in British First League. Yeah. Although running a lot is not being a good football player, because
Have you some application experience or some application of your performance analysis? After that, you will.
it has to be stable for some time.
Let's start the presentation again. It's open now.
Okay. Yeah. Very briefly, the results. This is spatial error, and you see the yellow bars are the GPS system, and they have rather big. And this is the mean spatial error, and they have 1 meter, about 1 meter error. And video is in between, and still with radar you have between 20 centimeter in the different courses. With the speed, you see the yellow bars are down in speed. GPS performs good with speed, and here the video system is the worst one. And these are the results, and you see here this is percent deviation from the gold standard in relevant categories for performance analysis. And you see that the GPS is performing very badly here. It underestimates the loads by more than 30%. Yeah? But also the video-based data in the high intensity things is more than 10% below the value of our ground truth. So there's room left for improvement in these devices, and it's a good idea to check it before you really take serious the results in practice. Good. I think we talked about this. Yeah, okay. So I will continue. And first thing, when you study performance analysis, a very important concept of our work is to distinguish between practical performance analysis and theoretical performance analysis. Yeah? And why is that very useful distinction? We have different aims in these two areas. Theoretical performance analysis, we want to analyze the structure of the sport, yeah? Influence in things, we want to analyze something like the nature of the sports. Yeah? And in practical performance analysis, we want to give support to the athletes. This is the aim, and from this, many differences are resulting. For example, research strategy. It's sort of basic research in theoretical performance analysis and evaluation research in practical performance analysis. We do here descriptive studies, and there we're interested in evaluating the process. From a methodological standpoint, very important. Here we have large representative samples, yeah? Let's say all the matches in the league, and here we're only interested in our club, yeah? Which is typically a single case and not suited for, let's say, classical statistical analysis, and we must be aware of this. And other things and that constitute a very big difference between those, and this is the consequence of this. If you are acting in this area of performance analysis, wherever that may be, you should be aware whether you are doing theoretical performance analysis or practical performance analysis to understand the two activities, because they are very much different. Sometimes people play both roles. Academics work with clubs or athletes, yeah? Or practitioners sometimes conduct scientific studies, yeah? But they have to be aware that these are different things, yeah? Different criteria for the quality and so on. And as far as I know, especially in this center, this distinction is very important. You do scientific studies as well as you're giving support to practice, and you have to realize it, that this is difference. And you have to be aware of the field you're working at, and one should not mix up the two roles. Yeah? So some ideas on practical performance analysis. Why do we analyze performances? It's not just to spend the time, but our purpose is when we analyze competition, we want to find out something that improves our training. Yeah? And this is the ultimate aim of practical performance analysis. And now you can say there are some steps. First of all, we have to have a good description of a competition. Yeah? Then we have to do our analysis. What are strengths and weaknesses of my athlete? Yeah? And then, can we improve this in training, transfer to training? And these steps are different problems and are to be addressed as a whole. And my message at this place is, if you do so in practical performance analysis, you are using qualitative methods and not only quantitative methods. Yeah? The qualitative methods, for example, content analysis, if you want to find out the content of a text of a book. Yeah, there are methods for it. Content analysis. First step is paraphrasing, then generalization, and then you reduce it, and then you find out the basic statements. This is a qualitative research method. Yeah, and when you see what are you doing in performance analysis and practical performance analysis, yeah, you have the source of information, video, and statistics maybe. You transfer it to the computer, and you extract interesting scenes, and you interpret interesting scenes, and then you reconstruct what happened and give an interpretation, strengths and weaknesses, yeah? And then, which is different, you have to validate it with a coach, for example, that there's an agreement on measurements to be taken, and you see the parallel structure, the parallel in methodology to qualitative methodology in the sense of content analysis. And now the coupling of competition and training looks like this. We typically have a quantitative pre-structuring, basic statistics, which give us a trace where to look at. And then we go into a deep analysis. We study the video scenes frequently, yeah, and find out the strengths and weaknesses. Then we go into a peer debriefing. We discuss our results with a coach, for example, or the specialists. And maybe there's an iteration also. We go again into the analysis. And then we develop an instruction in video training, and then prepare the players for training with instructions from video training. And then hopefully we get better prepared to competition again. So, a very important tool of computer science and sports to support this are the club management information systems. What we see in professional clubs, we have their data from many sources: match analysis, training monitoring, fitness training, medical, physiotherapy, psychology, and we have something like isolated information island instead of a club management information system. And this is a thing we are trying to do research on in sport informatics also. How should the club management information look like? You see here above you see the different sources of information. In the middle you see the central storage unit and retrieval unit. And below you see the different stakeholders that have some interest in the information. And ideally all the information needs of these stakeholders are fulfilled with this club management information system. And this is a central topic of sport informatics also, how to construct it, how to design it. What we know, what we suggest is to take a modular approach, to start with a certain area, yeah, and do the necessary steps to create a functioning module in a club management information system. Maybe then you go to the second area, third area, and so on, until you arrive finally at a web-based club management information system containing all the information modules you really need for your work.
And we may not be, let's say, naive. It's a big challenge because it's a large software engineering project. Yeah, it has a really big size. We have a complex system there with a complex system analysis, and we are working in a difficult setting. Professional football is a very difficult setting. Yeah, I tell my students frequently when they ask why are the coaches not interested in our nice analysis. Yeah. And say, what is the first problem of the coach in professional football? And the first problem is to be coach next week also, you know. And so this occupies them a lot, and only in the second row they're thinking about improvements in their job. We need experts from basic science and sports science, from informatics and sport informatics to do this. We need the specialists in practice for the single areas. And overall, we need a club management that's capable to run such a complicated process. Our experience are there are some commercially available products, but we are not aware in German Bundesliga about a really successful implementation where people really work with. It is very much superficial. One example, we realized as a module of a complex club management information system with a professional club. This is a module we call healthy reference pattern. And short definition, a healthy reference pattern is a battery of diagnostics that is periodically applied to all players for having a reference for prevention and rehabilitation process. Yeah, the idea is like follows. We have temporal, in intervals we have diagnostics. We collect the healthy reference pattern at time t and t+1 and so on a regular basis, half a year maybe. And now we have the individual prevention path. We have the results from the player. We can design the individual prevention for each player, yeah, until the next measurement, and maybe there's a correction then. But it becomes very important when we have to go to the injury path. The player is injured, yeah? And now it's very important for the physiologist to know how was he in a healthy state. This is the origin of the name healthy reference pattern. The physiologist in rehabilitation has a reference how the player looked like when he was healthy, yeah? And so he can individualize and has a very good data information base for the rehabilitation process. What we are doing with this German professional club, our healthy reference battery, is a gait analysis with EMG and force plates and Vican system. Then we do anthropometrics with this is a laser-based body volume system. We have isokinetic leg strength testing, and also jumping diagnostics. And this is the battery we are working it for creating the healthy reference for football players. Some results, we have very high muscular disbalances, quadriceps much stronger than hamstrings, and also the dominant, the shooting foot is stronger than the non-shooting foot. And also you can create individual profiles to find out the deficits and the strengths of a player. Too fast? Yeah. Now the presentation will be here anyway, yeah? So now, I hope I have some time to bring some idea about theoretical performance analysis, some reflections on the nature of the game of football, and of course, we are interested in parts of performance. How does it determine the whole performance, or performance prerequisite, endurance? How does it affect the performance? But we are also, a specialty of our group is that we are also interested in these can you start the video? Can you start it?
Swiss cutting the ball back and it's through. Oh, Shaqiri coming in. Corey Evans in the way. They're saying handball, and handball is given.
Okay, no, I can tell you. One example is, for example, the match Sweden against Italy. Yeah? Decisive match for the two teams to take part in the Russian World Championships. Yeah? And
Enough time.
okay, good. You make it in 5 minutes, right? No. And it decided it was a 1-0 in the match at Sweden and a 0-0 in the second match in Italy. Yeah? And when you see, so there was one decisive goal that decided that Sweden will be in Russia, participate in the championships, but Italy won't. And if you study this decisive event, you see that it was a deflected ball, yeah, that didn't have a chance to become a goal, but because it was deflected, the goalkeeper was not able to save it. Yeah. So what does this mean? What does it mean for the nature of this sport? Yeah? Italy is out. Italy is out. Sweden is in. And it was because of a deflected shot. Yeah. Okay. Play.
Swiss cutting the ball back and it's through.
I think it's now against Switzerland.
Wood Shaqiri coming in. Corey Evans in the way. They're saying handball, and handball is given. Are you kidding me? How can he give a handball when he's that close to him? Are you kidding? I just can't believe it. He's given him a yellow card as well. Unbelievable. He's like a yard away and he volleys it. And it's hit him on the shoulder. I can't believe that. Have a look at this. Well, he's turned his shoulder to... No trouble for Ricardo Rodriguez.
Will play here, Northern Ireland won't. Because of this single event, yeah? And it would have been correct if they wouldn't have been a penalty. Same in the match of Sweden. Ball was deflected and went in, and they couldn't. You cannot control deflection of a ball. Yeah. So, and it has much importance. So this is part of the nature of the sports. No, it's okay. It's okay. So, and it's very interesting to analyze football from this perspective also. For example, you can show that game intensity is an adaptive process. Yeah, for example, this team, FC Augsburg, was in this season the team with the lowest game intensity at home. Yeah? Now we have 18 teams in the first Bundesliga, and now look how the guests performed. The orange bar is the average away performance intensity, yeah, of the teams. But when they presented themselves at Augsburg, the team with the lowest intensity, yeah, all of them, except this team, performed below average. Yeah? That means the intensity is negotiated on spot. It's not a property of, it's not to be predicted from the endurance capacity, for example, but it's negotiated. Same the other way around. This is the team with the highest intensity. Interestingly, they were relegated this season. And this again, the orange bars, the average away performances of the teams. And you see they perform in general much higher when they are guests at the team with the highest intensity. So there's negotiation. Interaction between the intensities. So you have a match work rate, that is the intensity of a given match, and we analyzed one season with 306 matches. You have the season average team work rate. You have a home work rate, that's the average home work rate at home, and the average away team work rate away. And so these teams come together. And what they can also calculate is the interaction between home team work rate and away team work rate. Interaction is modeled by product here. And then you can see how much does the home work rate of the home team predict the match work rate, how much does the away work rate of the away team influence the match work rate, and how much does the interaction influence it. And you see here for 4 performance indicators that home work rate is very important to determine the match work rate. Away work rate of the away team is less important, but the highest importance is of the interaction between those, and this means teams come on the pitch and interact spontaneously, and you see the same scheme for all performance indicators. Another thing also, the pattern, the intensity pattern of matches. When you analyze the 5 minutes intervals, you have 18 5-minute intervals in 90 minutes, and of course you extract the net playing time when the match is running, and standardize it to meters per minute, and analyze the whole season. And if you say there is a typical course of a football match, yeah, then the assumption 1 is given. There's a typical course, and then we should have substantial autocorrelations because there is a typical change, stable change. And when you say each match is they are all fluctuating randomly, and the intensity is an emergent phenomenon, yeah, coming out of the situation, there would be no autocorrelation because these are random processes. And so we have here, this is the average intensity, distance covered of 306 matches, and you see some structure. Yeah? They're beginning very intensively, and this is reduced in the first half, and in the second half they begin again at a higher level, and then there's again a reduction. And this is the average of 306 matches. Yeah? And when you take the autocorrelation function, this is very well reflected there. You have here the substantial autocorrelations, and here again the higher ones reflecting the periodic structure of the first and second half. Yeah? But this is the average of 306 matches. Single matches look different. They look, for example, like this, or like that. Yeah? And you see, these are individual interaction processes, and when we calculate the autocorrelation functions per match, and then we take the mean value of the autocorrelations at the certain lags, it looks like this. We have the 1, of course, at lag 0, but then autocorrelation is disappearing when we calculate it per match, and this again is a hint that matches are unique interaction processes with emergent behavior. Okay, now my favorite study, chance influence in goal scoring. Yeah, again, we analyzed lots of goals, almost 2,000, and what we wanted to measure the involvement of chance in goal scoring. And then we defined some variables that were indicators of chance when a goal was scored. For example, when there was a deflection, like in the Swedish game, or when the rebound was converted from post or goalkeeper. You cannot calculate a rebound. Yeah? Or when there was a heavy goalkeeper interference. Yeah? You could not control, is it saved or will it be a goal? Then reflection from post bar into the goal and not outside. Rebound I was talking about, and from very large distance you need luck also to create a goal, and also when the defense has a ball contact prior to the goal, yeah, then it is not your plan. You cannot ask the defense for help in scoring a goal. Yeah? And when you analyze 2,000 goals, you find these percentages of these what we call chance variables, and you find that this sums up to 47% of the goals where at least one of these chance variables is involved. Yeah? And this is quite interesting finding what the nature of football is concerned, and if you compare the two leagues in a sort of stability testing, you find that these fractions are very similar in the two leagues, although they are of course completely independent, especially in the summative score. They are only 0.3% away, so this seems to be a quite
a quite typical property of football, that many goals, almost half of them, are scored with help of chance variables. And the result of a football match is weakly predictable, yeah, as you all know, but you can model it very simply. There have been, I mean, when this is the case where the home team has 4 chances and the away team has 4 chances, and there have been studies that show that on the long run there is a constant probability of converting a chance to a goal. Yeah? And if you do a simulation, of course, if the 2 teams have 4 chances, theoretically everything may happen between a 0-4 and a 4-0 with a certain probability, and you can easily simulate this with the binomial distribution. And so these are the probabilities of single results. Of course, it's very plausible that the 1-1 is the most frequent result, but it's only 17.8%. So not a good idea to bet exactly on a 1-1 in this case, yeah, because the odds are 17%. So in everything else is possible with a certain probability, of course. So now, if we score more, if we get more chances as home team, for example, this is a double amount, our winning percentage rises to 62%, which is not very impressive. Most likely result is a 2-1 for us, 13%. And now you can find out how many chances do we have to create to be sure to win the match. And here this reduces the percentage of losing below 5%. We need to create 15 chances when we allow 4 to the opponent. And to be sure to win in more than 95%, we have to create 20 chances. Okay, what is the consequence of the nature of a game? We have to see a football match as a unique, non-repeatable interaction process with an emergent dynamics and emergent results. And there are 2 possible attitudes towards that. Fatalism. Yeah? If it's chance anyway, I do not need to struggle, or I do not need to train. Maybe many football players say so. Or the other attitude is control. With sufficient effort, if we work hard enough, we will overcome these uncertainties, these properties. Yeah? So, and we can also think about, is this this nature of football, is this good or bad? Yeah? Is it something positive or not? Of course, coaches and also scientists want to have control, want to predict as much as possible, but the perspective of spectators and media is the opposite. They want to have exciting games, surprises, yeah? Big scenes, yeah? And tension. And this is why there is so much money in this sport, because there is surprise and tension and uncertainty, unpredictable things. Yeah? And for example, if you ask a coach, what is a good match? A good match is when nothing happens. We controlled the opponent, he didn't have any opportunities. Yeah? When you ask a journalist, say, this was boring, I didn't find a scene that was worthwhile reporting. And so the money is in the sports because of these exciting things that come from the nature of the sport, as I pointed out. So my personal opinion is, of course, we have to prepare as good as possible and play with biggest effort. We cannot rely on chance. Yeah? But also we have to be aware of emergent, uncontrollable nature. And my metaphor is to prepare for a football match, sharpen your weapons as good as you can, but be aware of unforeseeable events that may happen. Short conclusions. Performance analysis in football is a relevant topic for IX, Computer Science and Sports. We are dealing with introduction of new technologies. We develop software for practical support. We are modeling the nature of the sport with tools from there. For exerting practical impact, it is first, in my eyes, essential to distinguish between theoretical and practical performance analysis. It's necessary to adapt specific methods of analysis, for example, qualitative game analysis, and it's helpful to develop appropriate software support. And the theoretical challenge for theoretical performance analysis will be to grasp the nature of football as dynamic interaction process with emergent behavior. So, anything else we can discuss about later? Thank you very much and hope we see us in the final.
Thank you, Martin. Questions in English? Next presentation is Professor Dietmar Sauper from Constance University. Application of mathematical models for road cycling.
Do you want to have my laptop or my...
Yes. Ah, okay. Okay, so good morning, everyone. Thank you for coming to this lecture at the lunchtime. I realize we're all getting a little bit hungry, so I will try to be on time in 40 minutes and then take some questions. So my name is Dietmar Sauper. I'm from the University of Constance in Germany, and I am not a sport scientist, but I am from computer science, called Informatik in German. Now, I'm talking about our project. It is the PowerBack project that has been going on at the University of Constance and my group for a number of years. So for this presentation, I brought my own laser pointer, but I can see the technology is so advanced that this is outdated now. So we have to go back to the traditional pointers, which will work in any case, I hope. So when I talked to the people here yesterday and the day before, the first question that they ask me is, where are you from? And so I say, I'm from the University of Constance, and they say, Constance? Okay, so here I put together a map. So this is the map of Germany, and Constance is the dot, which is right here on the borderline. It's exactly between the screens. And so this is a picture of Constance. It's situated on one of the largest lakes in Germany, the Bodensee, Lake Constance. Constance was the center of the world 400 years ago, in 1614 to 1618 in Constance. This is a picture of that time, 400 years ago. The council of the Catholic Church was held at Constance on the lake for 4 years, from 14 to 18, and they made a very important decision. They decided to get away the 3 popes that existed simultaneously in the world. So the Catholic Church was governed by three popes, which were relevant for 3 parts of Europe. And then after this, there was only one more pope, only one single pope. Okay. So that was here. And nowadays, this is the view from our university overlooking the lake. Very nice. So it's a pleasure to be there, and I hope you will have a time to visit, and then look me up, please. I'll show you around. Okay, so I was asked to talk about modeling in sports science. So sports science, as you all know, is the process used to guide the practice of sport and to improve the performance, and models have a particular role in it. They promise, I say promise, not just provide, they promise to provide tools for analysis, prediction, and optimization of patterns in performance. So they go together, but there is a general consensus or a big problem of sports science in general and mathematical models in particular, namely that the transfer from sports science into practice is regarded as poor. It could be much better. The findings that we have from these analyses are difficult to implement in practice. And then often there's research that is completely irrelevant to practitioners. We do research and we go to the coach and say, well, look what we found. And the coach says, well, I can't use it. It's not interesting to them. So there is a need for institutions and also for funding for sports science research, of course, and also transfer to practice. And I'm happy to be here at this institute, this Center of Advanced Technology in Sports Science that may play a role, a lead role in the world to bring about new sports science research and also the transfer to practice, because you have all the connections to the athletes in the Moscow area at least, and also at the national level, I understand. Okay, so mathematical models and sports science, so I try to give some overview here. So statistical models are of very much importance. They can predict individual and team sport performance. For example, in basketball, they try to figure out what the performance of individual players or whole teams are in the next season. And it has been said that basketball, for example, is not a sport. It's a statistical network. So this is what the image is now for basketball in the public media, it seems. Then biomechanics, there was a session on biomechanics this morning here. So this is, as you all know, analysis and visualization of forces and resulting body motion. So you have a lot of differential equations in there. So these are mathematical models that have to be analyzed numerically, and then you get to optimize techniques and prevent injuries. Another type of category of model is fluid dynamics. So the analysis and visualization of forces and resulting body motion. So here in aerodynamic simulation, you can see the aerial pressure on the athlete and also the airflow around the vehicle, the obstacle here, the bike and the cyclist. And from these analyses, you can try to optimize the posture and design of the equipment and so on. Then a big category is performance models. I would like to classify it into 3 different regions. The first one would be the mini or micro region, physiological response to exercise load. That has been studied a lot. Heart rate, oxygen uptake, lactate, or even heart rate variability, as we've heard in an interesting talk just this morning. That determine fitness and health, and also just performance parameters. That's usually with constant work rate and does not generalize to full exercises generally. So the second category would be to optimize the performance for a complete exercise, which can be complex. So we're dealing with pacing strategies in endurance sports. And then one can go a step further, planning of training intensities and durations. Periodization is a keyword here, to increase fitness level, to prevent overtraining, to generate peak performance at the time of competition. So I thought maybe I should talk about details about all these different areas. but I decided just to focus on what we have done ourselves. So what follows is just our own work on oxygen uptake as a response to exercise and pacing strategies in endurance sports. And I will try to highlight all the points where the mathematical modeling comes in and is crucial for the analysis and development of the research. So this is an overview. I talk about oxygen update, our cycling simulator, how we generate pacing strategies for cycling time trials, and how we try to bring this into practice by a validation study. And then I conclude with my talk. So let's start with the oxygen uptake, respiratory gas exchange. So we're looking at VO2, CO2, the output, and these measurements can be made non-invasively, continuously, and they are precise, and I'm sure you have equipment for this in this center as well. And for these are important, of course, for endurance sports. These metabolic rates are the fuel and also the degradation product of exercising muscles. So here, for example, is a plot of the data. So the gray curve here is the power profile. So we have so it's 400 watts on a treadmill. Oh no, this is not a treadmill. This is a cycling simulator, an ergometer. So with increasing and decreasing demands, and then the reaction of the body in terms of heart rate, VO2 and VCO2 production is given in these curves, and you can see that they are sort of parallel to the load and to the power that is asked. So our task was to kind of predict what these curves are given the power profile. So the classical work, going back to Poole and Jones and many other researchers, of course, but they wrote a fundamental textbook on it, is as follows, that when you start to exercise at a constant load, your heart rate and also the oxygen consumption goes up exponentially in essentially 3 phases. The first very small phase initially, when at the onset of exercise, it's only a few seconds. Then there's an exponential major phase, the fast phase, which is also exponential. And then there's steady state, or at very high load intensities, there is a so-called slow component, which adds another third exponential growth component here. Okay, so this is the model, and then the formula for this would be like this. There's sort of a base level, at no intensity, and then there's 2 main components. The first component, well, the primary component, and then the slow component. And we're ignoring, as other researchers also do, this very fast thing here at the beginning. We say that, okay, we start here at this base level, not down here. That's quite common. And so we see that the major parts are linear combinations of functions that are exponential of this. 1 minus the exponent of t minus tk divided by tau k. Okay, so then the question is, what are these levels here of saturation? And for this, sports scientists have developed many studies and published them. And so for the first component, the fast component, as you increase the intensity here in watts, you have a linear ascent. These are the saturation levels in VO2 given a certain power. Okay. This is for just a ramp test, and then, but if you do the exercise much longer, at the severe rate, you go up to the VO2 max after a while. So these are these dots here. So we have modeled this with a function like this. So we have the linear increase here, and then this is the slow component that goes all the way up to VO2 max, and then there's a little transitional period here, which has been described by Poole and Jones, and they don't give the formula for this, but we did this here. This was our approach. You don't have to read this. It's this picture here that's implemented in the formula here. Okay, so then let's go back to these to this picture. So you see that these exponential increases here are of the sort, and what we observed is, well, that's quite well known from mathematics, that these exponential functions here are solutions of a simple differential linear equation. Okay, this is a linear differential equation. Mathematicians among you will know this, that you get these exponential solutions. So what we can do for the model that uses the constant work rate, so exercise at a constant work rate, 200 watts, 300 watts, or whatever, then you have these, then the model of Poole and Jones will hold. This is the solution again. Here you have these saturation levels, A of P, and so there's two components, the first one and then the slow component. And so you have a base level plus the first plus the second component here. And these two components are these exponential functions, and they can be written also as a solution of a linear differential equation like this. This is for constant power. Now what is happening if the power is changing, as in the real world in an exercise? If you're on the bike on the mountain, you're not going at constant power. It will change. So then the power depends on the time t here, and we can use this differential equation just by changing the constant power by the power function. Then we no longer have these exponential solutions here because everything is variable, but we still can say, okay, we have a base level plus the first component and the second component, and they are governed by the same linear differential equations. However, the right-hand side is time dependent. Okay, so in this setup, we have, this is a setup now, and we have parameters in there, 10 parameters that govern the whole scenario, we would say. So we would, in the practice, we would have to estimate these parameters, and then we can make predictions, marking and prediction. So this is what we have done, and then we have also another approach which does not use these linear equations, but just uses a black box model. For example, the Hammerstein-Wiener model, where you have as input your load and as output your VO2. And you can then try to model it with different nonlinearities in the input and the output, and also different linear systems in the middle. That's called Hammerstein-Wiener models. And so we tried this out with different options in MATLAB. And then one can apply it with different inputs and outputs. For example, the input could be either the power or the heart rate or the tuple, power and heart rate. And the output could be the VO2, the VCO2, or the heart rate. We can model all three of them with this, this process. And we have found by just brute force investigation that the unit gain, so that means the no input nonlinearity or just identity here will work best. And for a linear block, we use transfer functions of order 2 to 20, and the output nonlinearity was just piecewise linear. So for that, with these two approaches, the differential equations approach and the Hammerstein-Wiener model, we went to practice and tried it out and designed some tests on our hygrometer. So the first test was a step test until exhaustion. The second test was this profile that you have seen before in one of the graphs, where we have a long period at the end here until exhaustion. And then here we have another test where the intensity goes up here, and here we have 4 slots where we ask the participants to pedal for 10 seconds with maximum intensity. And here we have a course, sort of simulating a course. This is the gradient, so this is an uphill course with a steep gradient here at the end, above 10%, which is quite challenging for the riders. So with these 4 rides, we measured it on 5 healthy, some well-trained subjects, some not so well-trained, and figured out what the models would give us. So this is an example for the data that we have. We have the power here. This was on the right where we had the slope given. And so the gray stuff is the data, and then we have a Gaussian smooth curve for the power. And then over here is the oxygen consumption. The gray curve is the measured one. It's quite noisy, as you can see, and we have to smoothen it with a Gaussian filter with a sigma of 20 seconds. Okay, so now what is the performance of the dynamic models after fitting the parameters? Well, for the modeling of, say, VO2, we have a root mean square error and the mean maximum a percentage error of 0.09 and 3.1%. That's quite good. And then we also applied it to prediction. That is, we fitted the parameters on one of the tests and used this model then with these parameters to predict the performance on the other test. And then we change these tests around, of course. Then on average we get 0.3 liters per minute oxygen consumption as the root mean square error for the prediction. So modeling is better than prediction, of course. That's to be expected. Okay. And then the question is, how good are these results? Can we say, okay, we've done all we can and we're done, or is there still room for improvement? So for this, we look at the natural variability of oxygen consumption. So if you do one test today and another test tomorrow and another test the next day, your oxygen consumption, even at constant power rate, will not be exactly the same. There's a natural variability. So it does not make sense for our modeling to predict or to model better than what this natural variability is. We cannot expect that, right? Okay, so we measured this natural variability with 11 subjects, 2 identical cycling RAM tests to exhaustion on 2 days, and the result was that the root mean square error, the change between the different days, was 0.09 liters per minute, which is the same as what our modeling does. So we can say that the modeling with this differential equation approach, the dynamic model, produces a model that is as good as you can expect. So yes, we can say we're done with it. Now what about the Hammerstein-Wiener model or the Wiener model? There we have a modeling error which is even smaller, so 0.06. So this is also very good, even better for the modeling. But for the prediction, we have 0.27, which at the prediction here, well, it's also 0.30, so it's about the same. So they are roughly more or less equivalent, what the modeling and the prediction is. And here's an example of what we have for the modeling. So this is after parameter fitting. The VO2 measurements are the dotted black curve, and the other curves are the models that we get after parameter fitting. The dynamic model from the differential equation, and then these others are for the Wiener model using as data the power, the heart rate, or both. And you can see, and you could also see in the table from the numbers that the results are quite good for modeling. Now for prediction, it's a little bit different. Here again, the dotted black line is the oxygen consumption, and the others are the predictions, and we see that over the curve here, over the time, we are a little bit above the truth, and at the end there's even kind of an outlier here for the dynamic model, which indicates that our modeling is not yet perfect, and well, the error was 0.3 root mean square error versus 0.1 for the modeling. Okay, so this, in summary, what we have found is that the modeling that we can do with either model is as good as the natural variability. And for prediction, we can predict the VO2 with about 10% accuracy, the heart rate with 5% accuracy, and VCO2 with 15% accuracy. So when we compare the dynamic model with the Wiener model, we can see for the modeling that the Wiener model is to be preferred over the dynamic model. It has even a little more accuracy. For the prediction, well, I mentioned one number which was about the same, but when you look at the others, you find that the dynamic model does a little bit better job of the prediction than the Wiener model. The efficiency clearly is a win for the Wiener model. To train the Wiener model, it's very simple, but the dynamic model where you have to find the parameters, that takes much, much time. Inside, okay, what do you learn from the model? Well, when you apply the Wiener model, you get a black box. A black box is black. You cannot look inside. Or if you look inside, you see just garbage. You cannot interpret the numbers very well. But for the dynamic model, the parameters that you estimate have a meaning for sports science. Right? So these are time delays and so on. Okay, so I give 2 pluses for the dynamic models and 0 for the Wiener model. So for future work, we need larger, more diverse databases for training, and we can integrate special off-transient dynamics which were not modeled there. So the application of all this would be in our project to generate this. So while cycling, we could measure, for example, the heart rate or the power or both, and then we can estimate on a cycling trip what the VO2 consumption is of that particular estimate using this model, and then we could use it for training and prediction and optimization. Okay, now let us come to the second topic, the bicycling simulator. So in our bicycling simulator, here you see a picture of the simulator. We have a regular frame. We have here a brake unit, which is the most important central part of it. So it generates a braking force with an eddy current brake, which is under computer control. We have here an SRM where we can measure the power here at the chain wheel. We measure the pulse. We have gears. Actually, we use simulated gears, not the real gears. We have a control unit, a display, and also we can project it on the wall for a visualization of a real-world course. So now I'm going to explain how we built the simulator and what the modeling aspects there are. So I like to, in this overview, partition it into 4 different layers. We have a model layer. So there's the physical model of cycling. So this is mechanical. There's the visual and 3D model of the track. So we need to know where's the track going, what's the slope profile, and so on. Then we have a physiological model of the athlete, for example, where this oxygen consumption is modeled, which can be used then later in the application layer. So in order to drive these models, we need the parameters that come there. So we can use ergometer tests to determine physiological models, and I'm sure you do many of those here in the center. For the physical models, we can apply direct measurements, for example, the weight of the athlete and the bike. That's trivial. But also, perhaps one can use field rides out in the world and some model-based estimation techniques to estimate some other parameters here in the physical model. I'll get to that. We have GPS, that was mentioned before, and GLONASS, of course, which is implicitly implied here also. And with this, we can measure the course outline, but also some parameters of the physical model. We have a camera that records the track in video. So this is a parameter layer, and then there's a computation layer. So for the visual model, we have visualization, and we can run the visualization on our simulator. Now, at the end, which is not part of the simulator, that still is. So once we generate the simulator, we have field rides, and we can compare the two performances here. And our goal was to run the simulator such that it simulates the field ride as precisely as possible, and we would like to quantify this, just like you quantified the preciseness of your measuring devices that measure the position of the players on the field. We wanted to show our simulator simulates the real world accurately. So we have to compare it with some ground shows with field rides. And then, this is a topic after this, the pacing strategies coming up after the simulator. We use the physiological model and the physical model to optimize the performance, to generate pacing strategies that we can test in the field or in the simulator and compare them. Okay, so what is the basic model on the physics? Okay, it's a differential equation that relates all the resistance forces, overcoming potential energy, climbing a hill, okay, aerial resistance, going against the wind, rolling resistance in the wheels. No, that's on the surface of the wheel and on the road. Bearing resistance is inside the bearings, and overcoming kinetic energy, accelerating or decelerating. So these are the 5 forces. They make up together the resistance forces, and the athlete has to overcome these by pedaling. So this is a pedaling force. Okay, there are some factors here accounting for radii of the chain wheels and the radii of the wheels and so on, and the chain efficiency. So we have many parameters from the bicycle and the cyclist, many parameters for the course and the environment. All of these are required to run a simulation, of course. So here's a picture. And this is a model that we did not develop it, but we validated it. This is from Jim Martin and others in '98. Okay, so for the parameter estimation, what we cannot measure, we have to somehow estimate. And one way of doing it is to do this by field rights. And this, I think, is a new approach well, not entirely new. There are some people who have done similar things before. So here in the differential equation, which I've rewritten here, so here the left-hand side is now the the change of velocity over the distance, not quite the acceleration. And then you have here these parameters here that were in the equation before. There are 6 unknown parameters. And all the others that are here in black can be measured directly or are physical constants. So we can first summarize this by changing it a little bit, massaging it around to get 4 parameters, kappa 1 through kappa 4. Okay, and this equation must be holding for all different combinations of speed and power and so on. So what we can do is we can go out in the field and make a measurement of power and speed, and we have to estimate the parameters kappa, or the vector kappa here, and so we can compare the modeled speed v at the point x with the parameters kappa, and these are just the physical parameters that are fixed, and compare it to the modeled speed with the measured speed. This is the speed measured by our SRM system. And then we take the square difference and integrate this over the length of the course, and then we get something that should be as small as possible, j of k. And so one can use a MATLAB function or to minimize this sum of squares, and in it you have to compute the derivative of this functional, and you can do this by solving a particular differential equation. I don't go into these details. So in practice, there's a calibration track. For example, here, nearby Constance, this is the slope profile. It goes up and down just a little bit. And then we have a validation track where we try to figure out whether our modeling would be okay, also in the neighborhood. So on the calibration track, one rider went back and forth with different speeds. And so we have then the measured speed here in blue. And then we can run our simulation either with literature-based parameters, that's the green curve here, so it's off, or by our calibrated parameters that we take from the right and we minimize this functional j, and then we get the red curve here, which is very close to the measured one. Okay, so that's the modeling, and now for the prediction. So you go to a test track, a different track, and you do the same thing, go back and forth with varying speed, and you can run the model again and compare it to the measured one. And then we see again that the parameters that we calibrated on this track here also worked for the other one. These are physical parameters. That's a theory, and we find out that indeed it is true. Okay, so this was the physical parameters. We also have to measure the course. So there we use the GPS just as in soccer. Okay, but you can also use our bike computer to calculate the distance. One can use differential GPS, which is much more expensive and not portable, but that could provide some ground truth here. And now we devised a new method, that's namely the model-based calculation of the gradient. What we want to use, what we want to have with the GPS or all the others here, is the slope. The slope is the main determining factor of performance in a time trial where you go uphill. So we need to have the gradient very precisely, not just 5%, 6%, it would have to be 5.15% or something like this. So we can use our GPS data and the elevation in it as a first guess, and then we can use our differential equation model actually by taking the power and the speed that the athlete provides to solve for the slope. Namely, we can just solve our equation for the slope here. This is it. Here's the slope. We just treat this as an unknown. And then all the other measurements here that come in with our parameters kappa 1, kappa 2, kappa 3 that have been aligned already will give us an estimate of the slope. And that should improve, hopefully, the GPS data. And this is in fact true. As you can see here on the track, you can look at the power and the distance here. And so the power is the one that comes out from the equation. There's a measured power in black, And using just the GPS data, you get the blue curve. And using the modified elevation based on the model, derived from the model, is the red curve, and that matches the measured power much better. So it's a better estimate of our slope. Okay, how does the simulator work? Well, in the other equation, the big one that you have seen, we had the resistance forces on the one side and the pedal forces on the other side. So when you are on a simulator and you're pedaling, we can see how fast you're pedaling. That's easy. So the rotational speed is given, and that would determine the speed in the simulation. From the speed in the simulation, you can then figure out from this large equation what the pedaling force should be here, right, at that point. We want to simulate the real pedaling force. Okay, so the model calculates what the real pedaling force is, and then on the simulator, you somehow have to simulate that pedaling force. So this is done by the eddy current brake that puts a brake resistance here, and so that should match the pedaling force over here. We can computer control this brake force. And there's another term here. Maybe there is also inertia in here. There's a flywheel which has to be accelerated or decelerated. So that also contributes to the force that's opposing the pedaling force. So these two terms have to make up the pedaling force. Then aligned with some factors here as before in the other equation. So this is the way the simulator works. We know the speed from the rotational speed of the pedals here on the crank. The equation figures out what is the pedal force that is applied in the real world, in the simulation. And the brake then, we solve this then for the brake force and send the signal to the eddy current brake to apply that particular braking force, the resistance force. Okay, now how do we validate this simulator? Well, there's different ways to do this. Well, we have the mathematical model that does the prediction. We have rides outdoor, that is the ground truth in a way, and we have our simulator. And now let's say we apply a constant power. We tell the rider, here's the mountain ascent, go up there with a constant power of 200 watts or whatever. And we can ask the mathematical model the same thing. Apply 200 watts for this simulation. See what comes out. What is the speed at any point in time or any point on the track? And we can do this on a simulator also. We can ask the athlete, well, go with 200 watts and we'll control for this in the simulator and look at what the speed is that comes out. So this is what we have done. We could have done this also with constant speed and power output here, but we've done it the other way around. And so now the first, when we compare the model with the outdoor situation, the model should model the outdoor situation. We can see what the model comes up with the power and what the SRM measures as power, and these curves are hardly distinguishable. And here you can see a distribution of the deviations from minus 50 to plus 50 watts. And here are some numbers that quantify these differences. So the mean error, the mean absolute error is 8 watts. And then the next thing is we compare the model with the simulator. And there again, we have a close match. Of course, the simulator is built to simulate the model. Of course, it cannot do this 100% exactly. There are some limitations. And so we see a little bit of variation in the power here. And the limitation is that the eddy current brake cannot be controlled as exactly as we would like, perhaps. And there's a little bit of a bias in the ergometer. While up here the problems were that we have to estimate the parameters. This is not always exactly possible. And of course the model is an idealization. Higher order terms are neglected in it, for example. And as mentioned, the gradient accuracy is also of crucial importance, and our gradients are not 100% accurate, of course. But then the main test, of course, is again, how well does the simulator simulate the outdoor part? Okay, so there again, we run the test. We have one rider on the mountain track, and then we put them on the simulator and ask him to do the same thing, constant power at 200 watts, for example. And then we find out that the differences are also very small. We have only 7.5 watts of a mean absolute error. So this is just as good as between the model and the outdoor. So this is very good. And again, as for the case of the VO2 production, we had to find out is this all we can ask for, or can it be any better? And so we did an analysis and figured out what is the accuracy in the slope, in the GPS, in the other measurements of power, etc. We put all that together and then see what the natural variability is of the model power. We find out that it is of the same order of magnitude. It's also around 10 watts mean absolute error. So this is the only simulator in the world, as far as you know, cycling simulator that has been validated scientifically. All the other simulators out there in the world that you can buy from vendors in the industry, they're there to make it look good and feel good. But they're not scientifically validated like this one, where you can see, okay, this is really a simulation of that particular track outdoor that I know from my practice. Or this is not the simulation of the Rio de Janeiro time trial. This was one of the goals. Maybe we could have gone to Rio de Janeiro, measured it out, and then made predictions and could have trained athletes to go there. We're not so fast. Okay, now the next topic was pacing strategies. Okay, we have the simulator. Now the next question is, can we use our mathematical models to guide the athlete to arrive at the destination in minimal time? Okay, so we have a mechanical model that governs, you know, the bicycle, the environment and so on, the slope as before. We have a physiological model. I haven't told you the details about it. It measures the internal metabolism of the athlete and his capabilities, performance capabilities. And then we would like to devise an optimal control strategy. So there's a destination over here, the rider is over here, and along the track he should go with a certain speed or with a certain power output to arrive here in minimal time. So this is what we calculate. It's color-coded here. So go fast here, go slow here, right? And so the optimal control strategy is a function of time or a function of location along the track that prescribes the power output the athlete has to apply in order to arrive at the destination with minimal time. Of course, we cannot prescribe him to go with 1,000 watts all the time. You can go a minute or so or less with 1,000 watts. So there are limits which are governed by the physiological model, so we have to take care of that so that it all makes sense. So what is the physiological model? We use the critical power model. It's old-fashioned, but it has the advantage that it has only few parameters that we can fit. If we use more complex models like the Morton-Margarita model, it has 8 parameters or so, and it's very hard to validate and very hard to align. And we find that with the critical power model, we can generate satisfying results. So what is the critical power meter? We have an anaerobic work capacity. So this is what we have in our battery that we can use up in an exercise 100%, and then we are exhausted. Okay, so this is modeled by this vessel here, anaerobic capacity, the whole thing here. And it is fed by an unlimited vessel up here, and and the stream is just a critical power. So this is a certain number of watts that can be supplied to the system continuously. So if the athlete takes out of the system down here more than the critical power, this vessel drains, and when it's empty, the athlete is exhausted. If you take out less than the critical power, the vessel fills again, and you're recovered after a while. So this is a very simple model. There are 2 parameters in the critical power and the anaerobic work capacity. However, as we found out, this has a problem, namely it prescribes that, like for this suggested strategy, the riding strategy, over a few kilometers, that here within 90 seconds, a minute and a half, after the athlete is completely exhausted, he is recovered only in 90 seconds. This is not realistic. So we said this critical power model lacks the right modeling for the recovery phase. The recovery is slower than this. So the simplest remedy for this, of course, is to let the recovery be slower than before. So this is a function of the power, and here's the recovery rate. So if the power is above the critical power, we are exhausting our system. If we are below the critical power, then our old model prescribed the same rate of recovery as it would prescribe a rate of exhaustion for the same difference in power. So we just pulled the curve down a little bit. So we have a parameter alpha here, which is the a factor that we multiply with the rate. So that factor would be less than 1. If it's 1, it would be the same linear. If it's at 0, then we will have no recovery, or we would have immediate recovery. And then we have a continuous and differentiable transition like that. Okay, so we have a factor R alpha here of P of t, and R alpha is this function. So with this simple model, we can now generate more realistic recovery curves. So for example here, the colored curves are for different factors of alpha, and so the exhaustion is not complete here, and the recovery is slower. Okay, so now for the optimal control problem, what do we have? Well, we want to arrive at the destination with minimal time. So we set up a system of equations. So we have the speed, v, we have then the derivative, so this is an acceleration essentially, which is then governed by the physical model, the big equation that you have seen. So the variables are there, the speed, the location, and the power at time t. And then we have the anaerobic work capacity, En, or the remaining anaerobic work that we have there, and that is modeled by the physiological model the critical power model, the extended one. And the boundary conditions are that at the beginning, we are at point 0, at the end, capital T, we are at the finish line. At the beginning, the speed is V0, the initial speed, and at the end of the course, we should be exhausted. So the reserve, at the beginning, we should have the full reserve, and at the end, we should probably be exhausted. And on the whole time, during the course, the anaerobic energy that we have available is between 0 and the maximum. It cannot be above. And then we calculate the total time to arrive at the destination. That's t, and we should minimize this. But then there's another term here, epsilon times the integral of the q squared, and q is just the derivative of the power. So this punishes, relaxes the j in the sense that high variations in the power are punished. And that makes the problem as accessible numerically, and it's also more realistic because the athlete cannot go from 100 watts to 300 watts in 0.1 seconds. It's not possible. So our recommendations for numerical solution is we need a regularization to prevent oscillations. That's this q squared integrated. We should also substitute the speed by kinetic energy. I did not write that equation. We found out that this may help a lot. Should we parameterize by time or by distance? You don't know. We have to check both. There's no theory that tells you have to do it one way or the other. What tools do we use? We do not develop our own optimization techniques, of course, because this is a very difficult subject and it takes many man years to do this. So we rely on packages like gprops2 or falcon.m. And what is the runtime then? Well, it depends sensitively on case by case. So for example, on one course of 4 kilometers, we found out if we parameterize by time, gprops takes half a minute for the optimization, Falcon 10 minutes, and it's just the other way around if we parameterize by space, x. So there's a lot of experimentation when you do this in practice. So now we get to the validation. Igor, how much time do I have?
It's enough time.
Okay, so for the validation, there's like 10 more slides. The last ones will be fast. So here's the course. This is in Switzerland, in the Engadin. So this is the Fruela Pass. It goes, it's 12 kilometers long. The slope is always positive, up to 11.8%, and 923 meters going up. That's the slope profile. So it's variable slope. And then we have 6 subjects, and we do the test on our simulator. You can do our test on the simulator. We don't have to go out in the field because our simulator has been validated. It does a good simulation. So the first test is an incremental step test until exhaustion, and we use this for parameterization. Then we familiarize the rider with the Fruela Pass course, also until exhaustion, right? So we ask the rider to go up there and be exhausted at the end. After the rider has seen the pass for the first time, he can go up there again until exhaustion to go and to self-pace him so that he is doing, well, the pacing strategy that he feels is the best for him. And then we calculate the optimal strategy and give him the feedback on the simulator and tell him, okay, you have to go so and so fast, and if you're not doing it, speed up. So that's this strategy. And then we have a particular validation feedback strategy that we also ask him to write up there again with a different strategy. And the rider does not know whether he uses the optimal strategy or this validation strategy. It's a randomized and blinded. So the optimal strategy is one that follows a personalized optimal strategy based on this mathematical model. And the validation strategy is there to answer the question, well, if a rider is doing better with the optimal strategy, is this due just to the fact that he has a pacemaker in front of him? Right? The pacemaker says, go fast, or go slow down. So a pacemaker is always of an advantage, right? So if you're running and someone is cheering at you, you go faster. So if we just measure our time with the optimal strategy to find out it's better than without, it does not answer the question whether it's the optimization that really helped us. It could be just the fact that we have a pacemaker there that's firing the athlete up. So in the validation strategy, what we did was very simple. We took the optimal or the self-paced ride of one athlete. That maybe he took 10 minutes. No, he took 60 minutes. Okay, and the optimized strategy was maybe 55 minutes. Then we just increased the power level of the self-paced strategy such that the arrival time, according to the model, would be 55 minutes, the optimal time, but with his own strategy. So we're comparing two strategies that would give the athlete, would get the athlete to the top in 55 minutes, which should be optimal, according to the theory. One with the optimal strategy and one with his own pacing strategy. And then we're expecting, if the optimal strategy is the right one, that he can follow the optimal one, but not the self-paced one. Okay, so this was our test design. Quite interesting. I've never seen this before. So, all right. So here, for example, you can see what we did for the validation strategy. So the blue line here is a self-paced strategy. So watt versus distance. And then we just took the curve and shifted it up by a few watts. Right? So it's a little bit stronger over the whole time period. And then the athlete arrives at the optimal time at the end, according to the theory. Okay, so for the parameter error estimation, we use the steps test, the familiarization ride, and the self-paced ride to calculate all the parameters of the physiological model. Let me not go into the detail of this, but here you can see the parameters, the critical power. So you can see subject 1 was very well trained. He's a competing athlete. And here's one who's not so well trained. And these are the anaerobic energies, and these are these coefficients alpha for the recovery. Okay, so here's one example. So the optimal strategy is the red line here. So that, again, it's power versus time or versus distance. And you can see the blue strategy, or the blue line here, is the self-paced ride. So a rider seems to be more conservative than the optimal strategy initially here, but at the end he does a sprint, right? High wattage at the end. Okay, that's the difference between the optimal and the self-paced. Okay, so now here we have the results for all these 6 subjects here. The self-paced time is 43 minutes up to 1 hour 20 or so, and then this is the optimal strategy. So this was what was prescribed. This was so all these times were better than what the athlete could do. So the optimization said, calculated something, and the result was you can do better than what you think you can, and it also prescribed where to go with what speed. So these are the percentage, the difference in percentage. So minus means less time. Okay, and we could then see, okay, that all subjects were able to achieve these goals. They all were able to follow that, all of them. So the optimal feedback increased the performance. Okay, so then the question is this improvement due to the optimal feedback, or is it just due to the pacemaker, to the feedback? So we did this validation ride. Okay, and so here are the results for the validation feedback, and we can see here that the arrival time should be the same, and okay, the self-paced ride with this is the optimal time here, and that the validation feedback also required, and this says yes or no whether the athlete was able to achieve that goal, and so we have 3 times yes and 3 times no. So half of the athletes were able to do this pacing according to their own pacing strategy with the optimal time, but half of them were not able to do so. So this indicates that really the optimality of our calculations in fact did yield a significant advantage, because 3 athletes were not able to reproduce the optimal time with their own pacing strategy. So subject 5 is highlighted because that's what we're going to see next. So here is the optimal the self-paced ride and on the validation ride. So you can see that the self-paced ride was here, and on the validation ride, this was what the athlete could do. And up to here, and here the athlete was exhausted, or too exhausted to continue with the old fashion. So there was a decline of the power here, and the athlete did not get to the goal. So the pacemaker improved performance for most subjects, but three of the subjects, but 3 were not able to follow the pacemaker. So the optimal strategy has some advantages. So these are the results. The optimal strategy was computable, it was feasible, and it improved the performance, and it is better than a pure pacemaker improvements that you can. Okay, so this is the overview, and the question now is, what is next? Well, the next step, of course, is to take this out into the field, to bring this into practice. Okay, so and we have to develop a feedback system that's working in the field, not in the lab. How do we handle deviations from the optimal pacing due to wind, errors and parameters, and so on? That's the question we have to deal with. We also need precise slope profiles, and we need to maybe more adequately model fatigue and recovery. Later, maybe downhill sections and downhill curves. So this is a setup. This was the one below. So what we are working on now is a mobile device that that takes in our optimal control strategy, and it does measurements and also updates with model predictive control or PID strategies, how to change the strategy if there's deviation going on. So again, there we need the physiological model, the mechanical model, and some intelligence on the smartphone. So we're working on this now, and also we have made arrangements with professional athletes in Germany, with BDR, and also with a professional World Cup team, and we hope to be able to do this. So these are my acknowledgements. This work was done by many people in the past, and we have funding, and then there's papers that you can read online here at this webpage. So thank you for your attention, and I'm open for questions.
I have a question.
Yes.
So your research, your model is relevant to time trial race.
Time
trial. But you know, the cycling sports is more road races,
yes.
And that is why I would like to know your definition. What kind of a sport, team or individual road races, and is it possible to use your model in road races?
For road racing, where you have a peloton, for example, right? The model itself is not sufficient because there's no drag involved. You can drag behind another rider, and there's a psychological component, right? You have other riders around you, your own teammates, your competing teammates, and so there's interaction between the riders. This is not encompassed by the model. Okay, so far only very few people have tried what we're doing here. I think we're the first group that really tries to validate this out there in the practice, and I know only 2 or 3 other researchers that have done optimization strategy with mathematical methods like this, but none of them have gone to the next step, which would be what you're doing. We have done 2 little things. For example, if there are 2 riders out in front, and only 2, not 20, just 2, how can the trailing rider optimize his performance, by saving energy, by dragging behind, and when is the right point to overtake and go to the goal? We studied this using these modeling techniques, and we have done one other little thing, namely, if we have 2 cooperating riders. Assume you're at the Tour de France, and 2 riders decide to take off and escape the field. And they manage to do so. They are ahead of the field, and now they have to cooperate. How do they optimally cooperate? How long does the first rider have to be in front before the other should overtake? And what is the dynamics of overtaking? And there we found something interesting, that the overtaking is, the optimal overtaking according to the theory is somewhat different from what the racers are doing in practice. Namely, the leading rider has to slow down a little bit to let the other overtake. And they don't do this. They just keep on going, and the other one is overtaking. So yes, we have done only very small steps towards the general problem when many people race against many other people, right? And that's it's a big challenge. But before we tackle that big challenge, we would like to solve the easy problem, the low-hanging fruits, which are still very, very hard to get, which is time trial races out there in the practice. We want to bring this out to the practice of the athletes really, and work with world team athletes.
So your conclusion, your opinion, road races or road cycling races is a team sports or individual?
This is what we have done is for individuals, right?
Yeah.
And okay. It's a big challenge to do the optimization for a whole team. Maybe one other thing that I have seen out there in the works is when you train, you can optimize according to some criteria you have to decide on as a coach how to do a team training. So when you have one team of like 5 riders, when should one overtake the other so that the effect of training is the best? So that was one other work I have seen, and Jaitner did this in Dortmund. You know him. Yeah. Question?
If I'm not mistaken, you have different original equation, yes? Like matter physiology. Yes? It's enough?
Is it enough? You mean enough parameters?
Yes, yes.
Okay. As I said, there are different models. Our physiological model is a generalized critical power model. You can take the Morton Margarita model, which has 3 compartments.
Only power.
Yeah.
Only power. Explanation. Critical power and explanation. You have cycle state. And your state is the power and explanation.
Of the state in our system, the state variables.
3 equations.
Well, in the optimization we have 4. We have the position, we have the speed.
It's a state of equation. Your model. And 3 ordinary equation.
Well, there were 4 actually. One is the power, the speed, the position, and the energy. Thank you very much. Thank you very much.
Now, a short time, quick time. The next presentation, 2:40. Exactly. Юрий, сейчас вот